Record.
Do you finally want to understand regression analysis? Then this is the place for you. My name is Hannah and welcome to this full course about regression analysis. After what is between simple and multiple linear regression are. Further, you will be able to interpret your results, understand the assumptions for a linear regression, and also the use of dummy variables. And at the end, I explain to you the basics about logistic regression. And of course, I'll also show you how to calculate a regression easily online. Let's get started. A regression analysis allows you to infer or predict a variable based on one or more other variables. Let's say you want to find out what influences the salary of people. For example, you could take the highest level of education, the weekly working hours, and the age of people. Now you can investigate whether these three variables have an influence on the salary. If you can do so, you can predict a person's salary by taking the highest educational level, the weekly working hours, and a person's age. The variable you want to infer, the one that you want to predict, is also called the dependent variable or criterion. The variables you use for your prediction are called independent variables or predictors. Regression analysis can be used to achieve two goals. First, you can measure the influence of one variable or several variables on another variable, or you can predict a variable based on other variables. This is the second goal. In order to give you a feeling for this, let's go through some examples now. Let's start by measuring the influence of one or more variables on another. In the context of your research work, you might be interested in what has an influence on children's ability to concentrate. You're interested in whether you can prove that there are parameters that positively or negatively influence children's ability to concentrate. But in this case, you're not interested in predicting children's ability to concentrate. Another example would be you could investigate whether the educational level of parents and the place of residence have an influence on the future educational level of children. This area is very research-based and has a lot of application in the social and economic sciences. The second area, which is using regressions for predictions, is more application-oriented. Let's say in order to get the most out of hospital occupancy, you might be interested in how long a patient will stay in the hospital. So based on the characteristics of the prospective patient, such as age, reason for stay, and pre-existing conditions, you want to know how long this person is likely to stay in the hospital. Based on this prediction, you can, for example, optimize bed planning. Another example would be that as an operator of an online store, you may be very interested in which product a person is most likely to buy. So you want to suggest this product to the visitor in order to increase the sales of the online store. This is where regression comes into play. What we now need to know is that there are different types of regression analysis, and we get started with these types right now. In regression analysis, a distinction is made between simple linear, multiple linear, and logistic regression. In simple linear regression, you use only one independent variable to infer the dependent variable. In the example where we want to predict the salary of people, we use only one variable, either, for example, if a person has studied or not, the weekly working hours, or the age of a person. In multiple linear regression, we use several independent variables to infer our dependent variable. So we use the highest educational level, weekly working hours, and the age of a person. So therefore, the difference between a simple and a multiple regression is that in one case we only use one independent variable, and in the other case we use several independent variables. Both cases have in common that the dependent variable is metric, and metric variables are, for example, the salary of a person, the body size, the shoe size, or, for example, the electricity consumption. In contrast to that, logistic regression is used when you have a categorical dependent variable. So, for example, when you want to infer whether a person is at high risk of burnout or not. Whenever yes and no answers are possible, you use a logistic regression. So in linear regression, the dependent variable is metric. In logistic regression, it is categorical. Whenever the dependent variable is yes or no, you will use a logistic regression. Does one person buy a product, yes or no? Is a person healthy or sick? Does a person vote for a certain party, yes or no? And so on and so forth. In all these cases, it does not matter what scale level the independent variables have. They can be either nominal, ordinal, or metric. So as I just said, the scale level of the dependent variable can be metric, ordinal, or nominal in all three cases. So in the simple linear, in the multiple linear, and in a logistic regression. The dependent variable is metric in the linear case, and it is nominal or ordinal in the case of a logistic regression. It is important to know that in the case of a nominal or an ordinal independent variable, the variables may classically have only two characteristics, such as gender with male and female. If your variables have more than two characteristics, then you have to form so-called dummy variables. But we will talk about dummy variables a bit later. So now a quick recap for you. There is the simple linear regression, and the question could be, does the weekly working time have an impact on the hourly wage of people? The distinguishing point is that we have only one independent variable in this case. Then there is the multiple linear regression. A question could be, do the weekly working hours and the age of employees have an influence on the hourly wage? In this case, we have at least two independent variables, so for example, weekly working hours and age. And now let's look at the last case, which is logistic regression. Here the question could be, do the weekly working hours and the age of employees have an influence on the probability that they are at risk of burnout? In this case, burnout at risk has the expressions yes or no. So now I hope you got a first impression about what regression analysis is, and we'll move on to the linear regression now. Let's get started. As you already know, a regression analysis allows you to infer or predict a variable based on one or more other variables. But what is the difference between a simple linear regression and a multiple linear regression? Let's first start with the simple linear regression. The goal of a simple linear regression is to predict the value of a dependent variable based on an independent variable. The greater the linear relationship between the independent variable and the dependent variable is, the more accurate is the prediction. Visually, the relationship between the variables can be represented in a scatter plot. The greater the linear relationship between the dependent and the independent variable, the more the data points lie on a straight line. The task of a simple linear regression is now to determine exactly the straight line that best describes the relationship between the dependent and the independent variable. In the context of a linear regression analysis, a straight line is plotted on the scatter plot. In order to determine the straight line, the linear regression uses the method of least squares. Let's say a hospital asks you to give them an estimate based on the age of a person, how long this person will stay in the hospital after a surgery. The target of the hospital operator is to optimize the bed planning. In this example, your dependent variable, the one you want to infer, is the length of stay after surgery. Your independent variable is the age of a person. The equation that describes the model now looks like this. B is the slope and A is the receptor point. If a person would be 0 years old, which doesn't really make sense in this example, the model would tell us that this person stays A days in the hospital. In order to calculate the coefficients, the hospital must of course provide you with a sample of people where you know the age and the length of stay after surgery. By using your data, you could find out that B is 0.14 and A is 1.2. This is now our model, which helps us to estimate the length of stay after surgery based on the age of people. Now let's say a person who is 33 years old is registered for a surgery. Then we would put 33 for X. Our model then tells us that this person stays in the hospital for 5.82 days after surgery. Now, of course, the question is, how do you calculate the slope B and how do you calculate the intercept A? Usually, you use a statistics program like DataTab. In the case of simple linear regression, however, it is also quite simple to do this by hand. B results from the correlation of the two variables times the standard deviation of the variable length of stay after surgery divided by the standard deviation of age. A is obtained by calculating the mean value of the length of stay minus the slope times the mean value of the age. The regression line always tries to map the given data with a straight line as best as possible. Of course, this always results in an error. This error is called epsilon. Let's say we estimate the length of stay after surgery of a person who is 33 years old. Our model tells us that the person stays in the hospital for 5.82 days, but in fact, he or she stays in the hospital for 7 days. Then the difference between the estimated value and the true value is our error, and exactly the error epsilon. Now you have a good overview of what a simple linear regression is, and we proceed with the multiple linear regression now. Unlike simple linear regression, multiple linear regression allows for the consideration of more than two independent variables. As we already know, the goal of a regression is to estimate one variable based on several other variables. The variable to be estimated is called the dependent variable or criterion. The variables that are used for prediction are called independent variables or predictors. Multiple linear regression can be used to control for the influence of a third-party variable. Multiple linear regression is often used in empirical social research as well as in market research. In both areas, it is of interest to find out what influence different factors have on a certain variable. Therefore, the equation for a simple linear regression looks like this. We have one independent variable x plus the constant. If we now go the way of multiple linear regression, we have several independent variables. The first variable, the second variable, and the kth variable. The coefficients can now be interpreted similarly to the linear regression equation. If all independent variables are 0, we get the value a. If an independent variable changes by 1 unit, the corresponding coefficient b indicates by how much the dependent variable changes. Let's say x1 is the age of a person and b1 is 10. Then for every further year, y is increased by 10. If the person is 5, we have 5 times 10, which equals 50. So y is increased by 50. Before we now look at the interpretation of the regression results, I will first explain to you how you can easily calculate a linear regression online. In order to do this, simply visit Data tab. You can find the link in the video description and just copy your own data into this table. Then you simply click on the Regression tab. After you've copied your data into the upper table, your variables will appear here below. Now you only need to select your dependent variable and one or more independent variables. Of course, this dataset is far too small, but it just serves us as an example. Your own dataset may of course have several thousand rows. Let's say we want to find out what influences a person's salary, so we choose salary as the dependent variable. As the independent variables, we can now choose gender, age, and for example, weight. As soon as you've selected the variables you want to use, Data tab calculates a regression analysis for you. Since your dependent variable has a matrix scale level, a linear regression is calculated. Now you can see the results here. We will go through the interpretation of the results in detail in a moment. The good thing is the Data tab also helps you with the interpretation. So just click here. A multiple linear regression analysis was performed to examine whether male, age, or weight variables significantly predict salary. The regression model indicated that the predictors explained 48.99% of the variance, and a collective significant effect was not found. F equals 2.56, P equals 0.1, and R squared is 0.49. But let's now go into more detail about the interpretation of results. Your results will be presented to you in this form. You can now, of course, just use the interpretation in words on Data tab, but we'll go through each block individually. Let's start with the model summary. The multiple correlation coefficient R measures the correlation between the dependent variable and the combination of the independent variables. What does that mean? Here we see the equation for linear regression. Our statistics program, like Data tab, calculates the regression coefficients. Now you can sum up all the values, and with the summed values you can calculate the correlation with the dependent variable. This correlation is the multiple correlation coefficient R. Or to say it in other words, with the regression coefficients and the independent variables, an estimate of the dependent variable is calculated. R now indicates how strong the correlation is between the true dependent variable and the estimated variable. Therefore, the greater the correlation, the better the regression model. The coefficient of determination R squared indicates how much the variance of the dependent variable can be explained by the independent variables. Your dependent variable has a certain variance. The more of this variance we can explain, the better it is. Let's take the example of how long you stay in the hospital after surgery. Of course, not every person stays in the hospital for the same amount of time. So we have a variation, and it's this variation that we want to explain with the help of a regression model. If, for example, we can predict the length of stay in hospital very well with the age and the type of surgery, this R squared is very large. If we can even explain everything, the result would be 1. In this case, we could predict exactly how long a person will stay in the hospital after a surgery using only the age and the type of operation, and we can explain all the variance of the dependent variable. But of course, that doesn't happen very often in practice. R squared overestimates the coefficients of determination when too many independent variables are used. To fix this issue, the adjusted R square is often calculated. The standard estimation error indicates by how much the model overestimates the dependent variable on average. Let's say you want to predict the length of stay in days after surgery. If your standard estimation error, for example, is 4, this would mean that you miscalculate on average by 4 days with your prediction. Now, of course, your question to the hospital management would be whether an average deviation of 4 days is too much, or whether the hospital says, great, this enables us a much better planning security. So next, this table is displayed. Here, the so-called F-test is calculated. The F-test tests the null hypothesis whether the variance explanation R squared in a population is 0. This test is often not of great interest. The test is equivalent to asserting that all true slope coefficients in a population are 0. So B1 is 0, B2 is 0, and up to Bk is 0. In this case, since we have a very small data set in our example, the results show that the null hypothesis cannot be rejected. The p-value is greater than 0.05, and we assume, based on available data, that all coefficients are 0. So now we reach the probably most interesting table. Here we see the unstandardized coefficients, the standardized coefficients, and the significance level. Capital B, the unstandardized coefficients, are just the coefficients that you can put into your regression equation. So if we want to predict the salary, we have a constant of 1920, plus the value of the gender variable, plus the value for the age variable, plus weight. This allows us to use the unstandardized regression coefficients to build our regression model. If we want to predict the salary, we now only have to insert the variables. Beta are the standardized coefficients. Here you can see which variable has the greatest influence on the salary. In this case, age has the greatest influence on salary because beta of age has the greatest amount. And finally, we see the significance value for the coefficients. Values smaller than 0.05 are considered significant. In this case, we see that not a single coefficient is significant. What does that mean now? The null hypothesis in each case is that these coefficients are 0 in the population. If the p-value is greater than 0.05, we cannot reject this null hypothesis based on the available data, and thus it is assumed that the coefficients in the population are not different from 0, and therefore the variables have no influence on salary. Due to the fact that I've used a data set that is actually very small, it's difficult to reach significant values. Of course, when calculating a regression analysis, you also have to check the assumptions. If the assumptions are not fulfilled, you cannot interpret the results of the regression meaningfully. Therefore, we now take a look at the assumptions. The assumptions for the linear regression are as follows. There must be a linear relationship between the dependent and the independent variables. The error epsilon must be normally distributed. Third assumption is that there must be no multicollinearity or no instability of the regression coefficients. And finally, there must not be heteroscedasticity. The variance of the residuals must be constant over the predicted values. And now we'll go into each point in more detail. Let's get started. In a linear regression, a straight line is drawn through the data. This straight line should represent all points as good as possible. If the points are non-linear, the straight line cannot fulfill this task. Let's look at these two graphs. In the first one, we see a nice linear relationship between the dependent and the independent variable. Here, the regression line can be drawn in a meaningful way. In the second case, however, we see that there is a clearly non-linear relationship between the dependent and the independent variable. Therefore, it's not possible to put the regression line meaningfully through the points. Since this is not possible, the coefficients of the regression model cannot be interpreted meaningfully, or errors in the prediction can occur that are larger than expected. Therefore, we have to check at the beginning whether there is a linear relationship between the dependent and the independent variables. This is usually done graphically. The next requirement is that the error epsilon must be normally distributed. In order to check this, there are two ways. One is the analytical way and the other one is the graphical way. When using the analytical way, you can use either the Kolmogorov-Smirnov test or the Shapiro-Wilk test. If the p-value is greater than 0.05, there is no deviation of the data from the normal distribution, so it can be assumed that your data are normally distributed. However, these analytical tests are not used that often anymore because they tend to always attest normal distribution in small samples, and they become significant very quickly in larger samples, thus rejecting the null hypothesis that the data is normally distributed. Therefore, the graphical version is used more and more. For the graphical solution, you can either look at the histogram or better, the QQ plot. The more your data lies on the line, the better is the normal distribution. And now we come to the heteroscedasticity. Another assumption for the linear regression is that the residuals have a constant variance. Since your regression model never exactly predicts your dependent variable in practice, you always have a certain error. Now you can plot your dependent variable on the x-axis and the error on the y-axis. The error should scatter evenly over the whole range. Then homoscedasticity is present. However, if the results look like this, then we have heteroscedasticity. In this case, we have different error variances depending on the value range of the dependent variable. This should not be the case. And before I show you how you can check the assumptions online, we now come to the last assumption, which is no multicollinearity. Multicollinearity means that two or more independent variables are strongly correlated with each other. The problem with multicollinearity is that the effect of individual variables cannot be clearly separated. Let's look at the regression equation again. There we have the dependent variable and here the independent variables with the respective coefficients. So now, for example, if there is a high correlation between x1 and x2, or if these two variables are almost equal, then it is difficult to determine b1 and b2. If both are completely equal, the regression model does not know what b1 and b2 should be. This means that the regression model becomes unstable. If you want to use the regression model for a prediction, it does not matter whether there is multicollinearity or not. In a prediction, you're only interested in how good the prediction is, but you're not interested in how big the influence of the respective variables is. However, if the regression model is used to measure the influence of the independent variable on the dependent variable, there must not be multicollinearity. And if there is, the coefficients cannot be interpreted meaningfully. So now the question is, how can we diagnose multicollinearity? If we look at the regression equation again, we have the variables x1, x2, up to the variable xk. We now want to know if x1 is quite identical to another variable or a combination of the other variables. In order to do this, we simply set up a new regression model. In this new regression model, we take x1 as the new dependent variable. If we can now predict x1 very well by using the other independent variables, we don't need x1 anymore because we can use the other variables instead. If we would now use all variables, it could be that the regression model is unstable. In mathematics, we say that the equation is overdetermined. We can now do this for all other variables. So we estimate now x2 by using the other independent variables, and we estimate xk by using the other independent variables. For all k regressions, in this case we have k new regression models, we calculate the so-called tolerance or the VIF value. The tolerance is obtained by taking 1 minus r squared, which is the variance explanation. Once again, the variance explanation indicates how much of the variance of x1 can be explained by the other variables. The more it is, the more one speaks of multicollinearity. If these variables can explain 100% of the variance of x1, then we no longer need x1 in the upper equation. If the tolerance is less than 0.1, you have to be careful, because in this case we could have multicollinearity. On the other hand, we have the VIF value. The VIF value is calculated by dividing 1 by the tolerance. Accordingly, you have to be careful if the values are greater than 10. And now I will show you how you can test the assumptions online. If you want to test the assumptions online with DataTab, you only need to select your variables and then click on Check Assumptions. Now you see a nice overview of the results here. You can check the linearity, the normal distribution of the error, the multicollinearity, and the heteroscedasticity. It's very simple, just try it yourself. Now it's time to look at dummy variables. You have to use dummy variables if you want to use categorical variables with more than 2 values as your independent variables. As independent variables or predictors, either metric or categorical variables with 2 expressions can be used. Of course, it's also possible to use variables with more than 2 categories, and I will explain this to you in the next slides. Categorical variables with 2 characteristics are also called dichotomous. An example would be gender with the categories male and female. Let's say you coded female as 0 and male as 1. In this case, female would be the reference category. If we now look at the regression equation and say the variable x1 is gender, then b1 is the regression coefficient for gender. Now, how can we interpret b1? We said 0 is female and 1 is male, so we just put that in. Then we have 0 times b1 for a female person and 1 times b1 for a male person. Accordingly, b1 indicates the difference between male and female. Let's say we want to predict the income of a person, so y is the income. If a person is male, this person earns more by the amount of b1 than a woman. If the person is male, there is a 1 here, and we have 1 times this value. If the person is female, there is a 0 here, and we have 0 times this value. If b1 is 400, for example, then it means that men earn 400 euros more than women according to this model. Now we've discussed how to handle variables with 2 values. Further, we should look at what we do when we have a variable with more than 2 values or categories. Let's say you want to predict the fuel consumption of a car based on its horsepower and the vehicle type. And let's say there are only 3 vehicle types: sedan, sports car, and family van. Thus, here we have a variable vehicle type with more than 2 characteristics, but for a regression model, we need a categorical variable with 2 characteristics. Therefore, the question is now, what should we do next? In order to use categorical variables in a regression, we have to create dummy variables. This means that we simply create 3 new variables. Each new variable has 2 characteristics. These characteristics are 0 and 1 or yes or no. So here we have our vehicle type with the characteristics sedan, sports car and family van. Now we create one new variable for each characteristic. So first we create the variable, is it a sedan, yes or no. Second would be, is it a sports car, yes or no. And our third variable asks, is it a family van, yes or no. So before we had one variable and now we got three variables which are dichotomous and therefore they all have only two characteristics. And these three new variables can now be used in the regression model. So the next question is now, what does that mean for the data preparation? You originally have one column with the vehicle type where the individual vehicles from your sample are listed. The first is a sedan, the second is also a sedan, the third is a sports car, and so on and so forth. Out of this table, you create your three new variables. What is the first car? A sedan, so you put a 1 here and a 0 for the others. It's not a sports car and it's not a family van. The second one is also a sedan, so we'll put a 1 here again. And the third one is a sports car, so we'll put a 1 here, and the others are 0. By continuing this procedure, we have finally created our new dummy variables. Now there's only one important thing to note. The number of dummy variables is always the number of characteristics minus 1. Why is that the case? If we know that it is a sedan, we are sure that it's not a family van. If we know that it is a sports car, we can also be sure that it's not a family van. And if it's not a sedan and not a sports car, we can be sure that it is a family van. Accordingly, one of the three variables is not needed because this information is redundant. Therefore, n-1 dummy variables are created. So in this case, we only need the dummy variable, is it a sedan or is it a sports car? Of course, you can also drop sedan and use the other two. And now I show you how you can create the dummy variables online with Data tab. In this example, we use salary as our dependent variable and as independent variable the age and the company. The variable company here has three characteristics: BMW, Ford and GM. Now we can see that Data tab automatically creates the dummy variables. Once we have the age and once the new dummy variables, is it BMW and is it Ford? Since we only need n-1 dummy variables, the last category was dropped. If your dependent variable is categorical, then you need the logistic regression. And logistic regression is what we are going to look at now. In the previous part, we discussed linear regression. In a linear regression, the dependent variable is metric. For example, it could be salary or height. Now let's look at the logistic regression. Here, the dependent variable is a categorical variable. Let's say you want to predict whether a person is at risk for burnout or not. You want to make this prediction by asking a person's highest educational attainment, weekly working hours, and the person's age. Since the variable whether a person is at risk for burnout or not is a categorical variable, you have to use a logistic regression. The logistic regression is a special case of regression analysis, and it is calculated when the dependent variable is nominally or ordinally scaled. Let's look at a few examples first. For an online retailer, you need to predict which product a particular customer is most likely to buy. In order to do this, you receive a data set with past visitors and their purchases from the online retailer. In this case, you need a logistic regression because your dependent variable is a categorical variable, namely, which product is a particular customer most likely to buy. The second example comes from the medical area. You want to investigate whether a person is susceptible to a certain disease or not. For this purpose, you receive a data set with diseased and non-diseased people, as well as other medical parameters. Again, in this case, you need a logistic regression because a dependent variable is categorical and it asks, is a person susceptible to a particular disease or not? And the last example comes from politics. The question could be, would a person vote for party A if there were elections next weekend? So again, a categorical dependent variable with yes and no as response options. What is logistic regression now? In the basic form of logistic regression, dichotomous variables, that is, variables with the characteristics 0 and 1, or yes or no, can be predicted. For this purpose, the probability of occurrence of characteristic 1, which is characteristic present, is estimated. In medicine, for example, a common goal is to find out which variables have an impact on a disease. In this case, 0 could be not diseased and 1 diseased. And the influence of age, gender, and for example, smoking status on this particular disease could be examined. Let's look at this in a graphical way. So we have our independent variables age, gender, and smoking status, and we use these three variables in order to predict whether a person is likely to get a certain disease or not. So the dependent variable is, will the person get a disease or not? So maybe now you might ask yourself the question, and why do I need a logistic regression for this? Why can't I just use a linear regression? A quick recap, in a linear regression, this is our regression equation. Now we have a dependent variable that is 0 or 1. Therefore, no matter what value we have in a dependent variables, we always get either 0 or 1. If we are using a linear regression, we would simply put a linear straight line into these points. The graph shows that values between plus and minus infinity can now occur. The goal of logistic regression is to estimate the probability of occurrence, not the value of the variable itself. So we want to know how likely it is that a value of 1 will be the result of the given values for our independent variables. The range of values for the prediction is thus restricted to the range of 0 to 1. In order to ensure that only values between 0 and 1 are possible, the logistic function is used. The logistic model is based on the logistic function. The important thing about the logistic function is that only values between 0 and 1 are possible. So no matter where we are here on the x-axis between minus and plus infinity, we can only get values between 0 and 1 as a result. And that is exactly what we want. The equation for logistic regression now looks like this. We have 1 divided by 1 plus e to the power of minus z. For z, we now use the usual equation from the linear regression, which is the equation here below. b1 to bk are the regression coefficients, and a is the on point, x1 to xk are the independent variables. After we insert all that, our logistic function looks like this. Now we need to determine the coefficients so that our model best represents the given data. In order to solve this problem, we use the so-called maximum likelihood method. There are good numerical solutions that help us solve the problem. So usually we just use a statistics program and it will give us the values b1, b2 up to bk. Finally, I will now show you how to calculate a logistic regression online with DataTab. In order to do this, you just visit datatab.net and you copy your own data into this table. When you select a categorical dependent variable, a logistic regression is automatically calculated. Let's say your dependent variable is a person buys a product or not, with the expressions yes and no, and the independent variables are salary and age. After you click on the variables, a logistic regression is automatically calculated. And now you get the results, which you can see below. The first table is the so-called classification table. This table tells us how well we can classify the categories with the regression model. After that, we get the model summary and the coefficients. I hope you liked this video and see you next time.